So today, myself and my colleague Moran are going to discuss what we do at Diagnostic Robotics in order to improve healthcare using AI methods. So I'm going to start by a quote by a famous American journalist. America's healthcare system is neither healthy, caring, or a system. So of course he's exaggerating by it. I guess you might have the same feelings for the Israeli healthcare system and even more for the American one. And we're going to show you how at Diagnostic Robotics we do everything we can in order to make healthcare more accessible, more cost effective, and eventually benefit the patients. So today we're going to talk about two different problems we're trying to solve in the company by using machine learning models. And we're going to start with the population health AI solutions. So in order for you to understand the problem, imagine that we could predict hospitalization of chronic patients or any deterioration of the chronic patients, catch this in the right time and match them to a correct intervention program that is supposed to lower the risk for hospitalization. So this is what we try to do, to build a predictive model to see which patients have a high likelihood to be hospitalized. So how do we do it? In Diagnostic Robotics, we work with billions of historical medical visits worth of data, which is a great potential for AI. And the data we're working with to solve this problem is claims data. So claims data is pretty similar to what was discussed about EHR data. It's a form of administrative data. Let's assume a patient goes to his doctor, and after visiting the doctor, he pays, for example, $100. Now he has the chance to claim the insurance company back these $100. And these claims contain information about pharmacy, lab tests, diagnosis, and procedures. Unlike the HR data, is even more noisy. So I want to show you a suggestion on how to attack this new data, and you can use this solution for any sort of time series data you have in your job. So the concept is called medical code embeddings. It might be very familiar to you from word embeddings. So we have billions of medical codes, and we can treat them as a time series of procedures, diagnosis, and pharmaceuticals, for example. In the medical world, we take these medical codes and move them to a higher hierarchy in order to simplify the medical content. And then we split the timeline for each and every patient, treating each and every patient as a single sentence, if I'm taking it back to the NLP world. So each and every patient is treated as a sentence, and now we can use word2vec or any kind of advanced language modeling in order to create the embeddings of those codes. And here you can see a regular example of how when we look at, for example, PTCA, which is a procedure related to the heart, all the nearest neighbors of this embedding are procedures, diagnosis, and pharmaceuticals that are related to heart failure. And by using these embeddings, we can build sequential models which improve the precision at K for all different top Ks in the ranking, compared to traditional logistic regression models without the code embeddings and without the sequential architecture. So now that we understood how we build these risk score models, I want to move to a different source of data, which is called the intervention data. So remember, we said we don't only want to rank the patients from most likely to least likely to have an hospitalization, we also want to match each and every patient to the right intervention in order to avoid the next hospitalization. So an intervention data includes information about when and how long did the patient engage in a program that is supposed to lower his or her risk. So now we enter the world of causal machine learning, which is a very interesting world because usually in machine learning, we only do correlations, and we know that correlation don't always imply causation. And we want to measure the impact of those intervention programs. So imagine that you have this crazy COVID virus, which we currently have, and there is finally a vaccine. So in order to first understand what we do, let's go back to the medical world. So in the medical world, in order to test a vaccine or to test anything, what they usually do is what we call randomized controlled trial. They take a group, they divide it randomly into two. One group receives the intervention, in our example, receives the COVID vaccine, and the other group doesn't receive anything or receives a placebo. And then we compare the outcome of the two groups on average. And let's say we want, our outcome is, did this patient have a respiratory hospitalization after receiving the COVID vaccine? So we compare the group from the intervention to the one in the control, and we calculate what is called the average treatment effect, which is the average of the difference between the two outcomes of the groups. Now, we're data scientists. We want to do a retrospective experiment that is based on data, which is cost effective and which doesn't discriminate a part of the population. So the fundamental problem of causal inference is that we can only observe one of the two outcomes. A patient cannot have the COVID vaccine and not have it at the same time. This is the fundamental problem. And I want to ask you, can we compare the hospitalizations of patients that received COVID vaccines to the ones who didn't in the entire population? And the answer to the question is no, because let's even take it to the extreme. Let's go back to January, where only people over 60 or with some chronic conditions received the vaccine. So if we were to compare this group of old people and sick people to a healthy group, we could have the misleading conclusion that the vaccine causes more respiratory hospitalizations. So what we want to do is to turn this observational study into a pseudo-randomized trial. So how can we do it? We have the treatment group. We know which patients went through an intervention program, and we try to find a new control group from the patients who didn't receive the vaccine by matching each and every one in the treatment group to his most identical twin in the control group in terms of medical features and demographic features. So let's formulate this problem. We have the confounders, which are our features. For example, the age and Charlson score, which is how sick the person is, in other words. And we have the outcome, which is preventable hospitalization. This path is what we previously did by building the risk score model. And now we have this thing, which we call the treatment or the intervention, and which is both affected by the confounders and both affecting the outcome. And we want to ask, does the treatment really affect the outcome like we want to? And our goal, if I go back now formally, is to have no statistical significance between the treatment group and the control group. So what's the easiest solution? Do nearest neighbor matching. So let's say we had these two features, age and Charlson comorbidity index. We can use, for example, Euclidean distance and find the nearest neighbor for each patient in the treatment group. And then compare the average treatment effect of the red dots versus the blue dots. But why give each feature the same importance? We have thousands of features, and we don't want to give them all the same importance. So here I want to suggest you one of the solutions that works really well for average treatment effect, and is what we call propensity score matching. So in propensity score matching, what we do is we build a model not to predict the outcome, the hospitalizations, but to predict if a patient will be assigned to the treatment, yes or no. So we can use any machine learning model to build this propensity score. The propensity score can also be a vector or a number. And after we have this propensity score, we do, again, this matching of the most identical twin, but now we capture all the features of the patient in a weighted way that is relevant to the treatment. And now again, we calculate this average treatment effect to measure the impact of the intervention. So I hope this was helpful. And if you have any causal problem at your work, you might consider the propensity score matching idea. And now I'll pass to my colleague, Moran.
Thanks, Noah. So I will talk about our second product in the company, our second problem that we want to solve. And this problem deals with a patient that already suffers from a problem, and we want to treat him in the best way. So the main idea here is that the patient fills out our questionnaire, our automated questionnaire, and then his answers is inserted into machine learning models, into AI system. And we do all the magic here, and then the output, we extract the output into a doctor dashboard where we suggest the doctor recommendation for treatment, resources, and diagnosis, and that are relevant for the patient, for the case of the patient. So how we do it? So in order to build ML models, we use textual data. Why we use textual data? Why we use NLP? So to build great ML models, we need millions or thousands of questionnaire answers, which we do not have right now, but we do have millions of medical visits text. We have retrospective data of medical records with text, and we can use this text in order to answer the questions of our questionnaire. So the main idea here is to take all the unstructured data, all the textual data, and extract concept from this text. For example, a concept can be a symptom, cough, chest pain, fever, and then we extract all the concept and get a structured data of a matrix, which each one of the vectors in the matrix represent a patient or a visit or the patient visit with a vector of concept that are existing in this visit. For example, if we have cough in the visit, we will have highlight one here in the vector that tells us that this concept exists in the case. So let's take a look on this example. We have the text, and we would like to find the condition of the patient in the text. The patient has a condition of psychiatric illness. We would like to find out what are the medication that the patient is treated with. Okay, we would like to find out what are the symptoms that the patient suffers from. For example, here we have the headache as the main symptom, but except from finding the symptoms that the patient has, we would like to find out what are the attributes of this symptom. The attributes that describe the symptom, for example, can be the location of the headache, which can be anterior in this case, the sensation of the headache, which is heavy, the duration of the headache, which is several months. All of these attributes can make our ML model more accurate, and we would like to find out all the attributes that describe the symptoms in the most accurate way. Another feature that we would like to find in the text is the value of the concept. Concept can be mentioned in a positive manner or a negated manner. For example, fever or visual disturbance are negated in the text because of the word without. So it's very important for us to find the value of the concept as well. Okay, so we have a huge pipeline to extract concepts from the text and then insert this concept into a machine learning model. I will talk in this lecture about two of our main classifiers. One is the entity relation classifier, and the other one is the negation classifier. So what is the entity relation classifier? So as I mentioned before, we would like to find the attributes that describe the symptoms of our patient. So if the patient have headache or chest pain, we would like to find the attributes that, which can be the location, the duration, and the value of this attribute. Where is the location, and how much time the patient suffers from this symptom. And if we have this sentence, for example, the patient suffers from headache and stabbing chest pain, we would like to find out that stabbing is related to chest pain and not to headache. So we would like to build an ML model, okay, that tells us the classification for two entities, if these two entities are related or not. So in this case, we would like the model to tell us that chest pain and stabbing are related, but headache and stabbing are not related. So how we build such a model? So we use Google paper that was published in 2019. The model used deep learning models in order to predict if two entities are related or not. And they present a few models in order to do that. I will talk about the last model they present in the paper because this model gave them the best results. So the main idea of the model is to use markers. What are the markers we use? So first we use markers for the start and the end of the sentence. And the important markers are the markers for the entities. So we have start token E1 to start the entity 1, and end of E1 to end entity 1. And same we have two markers for entity 2. We have E2 as start marker for entity 2 and end of E2 as the end marker of entity 2. And then we can extract the we can insert the modified sentence into a BERT or a BERT model that give us the contextual embedding of each one of the words in the modified sentence. So we use the contextual embedding of the start marker of entity 1 as representing the entity 1. Okay, entity 1 can be multiple words, for example, chest pain. So we have E1 as describing the representation of the two words of entity 1. And we can take the contextual embedding of the start marker of entity 2 as representing entity 2 in the text. So we have the two representation of the two entities, then we can concatenate them into one vector that describe the relationship between them. This vector can be inserted into a dense layer and then a softmax to classify if there is a relation between the two entities or not. So we use this model in our system, and this model gives us very good results. Another classifier that we use is a negation classifier. The main idea here is that we have a concept in the text that we want to find if they are positive or negated. For example, without fever or visual disturbance. So the word without makes fever negated. And visual disturbance is negated as well because the word or continues this negation. The patient does not mention fever, but mentions cough. So fever is negated because of the words does not. And cough is positive because the word but cancel this negation. The patient denies fever, vomiting, nausea, and blurred vision. So all of these concepts are negated because of the word denies. But the word feels makes dizzy as positive. So how we can build a model that tells us for each one of the concepts in the text if they're negated or not. So in order to do that, we use masking mechanism. So the masking mechanism helps us in two issues. One issue is to tells us it tells which one of the words in the sentence are now on focus. So now in the first sentence, we can see that fever is now on focus. So we use masking for the word fever, and the label is related to the masking word. So we have negated the label for the word fever because we know it is negated. And in the last sentence, we can see we use masking for the last word, for dizzy, which the label is positive. So this is the first use of the masking mechanism. Another issue that the masking mechanism helps us is to generalize the model, to tell us which word is in focus, and except this, it's generalized the model in terms that it doesn't matter for us which word is behind the mask. If it's fever, it's vomiting, it's nausea, it doesn't matter. What is matter is the pattern of the sentence and how the masking is and where the masking is mentioned in the sentence. Here you can see that the denies becomes before the masking word. So we know that we expect the masking to be negated. We can insert these modified sentences into a bidirectional STM with attention or transformers with a softmax that tells if the sentence with the masking is negated or not. And this kind of model, you can use it in a variety of tasks, but it gave us very good result as well. So how do we use all these concepts in our system? So we take all the concepts we extract from the textual data, and then we can train a machine learning model to predict which diagnosis the patient has. So if we take a look on this patient, 25 years old, healthy, with left-sided frontal headache, stuffy nose, vomiting, we can extract all the concepts from the text, and then we can predict what diagnosis the patient might have. So sinusitis, for example, is in the first recommendation, then headache general, and we can use the concepts to get the reasons that led the model to give us this diagnosis. So the model thought that the patient suffers from sinusitis because he had a cold and stuffy nose, headache worsening when leaning head forward. So all of these attributes gave us these results. And after examination of ENT and evaluation of CT, this patient was really diagnosed with acute sinusitis. So in this case, our recommendations were good. And that's it. Thank you. I hope you enjoyed our lecture. Thank you, WiDS, for letting us talk. And if you have questions, you can send us a mail or ask now.
Thank you, Moran. I have two questions actually. The first one is, which sequential models did you use for predicting hospitalizations of patients? And the second one is, which model can be used for propensity score calculations?
So the sequential models we used are both LSTM and CNN. And for propensity score, you can use any model. Even better to use a non-linear model, so the more complex ones.
Okay, and when turning the treatment's timeline into word-to-vec, how do you treat, if at all, the spaces, time between treatments?
That's a very good question. So what we do is we divide the timeline into buckets, and then we can treat each and every bucket as a different time frame.
Okay.
I'll be happy to elaborate more. You can contact me.